Hello everyone, welcome to Station Boy. So today we are going to learn about AC circuit fundamentals. I decided to divide this series into part 1 and part 2 so it will be easier for you guys to understand. So let's delve into it. So over here you see a standard AC waveform. On the x-axis you have time and on the y-axis you actually have your voltage. We are going to use sine wave because I just want to put out the concepts that are used in AC circuits. We also have sawtooth and different types of waveforms, but for this video I'm just going to stick to sine wave. So the electricity that actually comes to our house is basically because of, like you can say AC current. It's actually much more efficient than DC because like in transmission wise DC has too much of drop over the long lines. AC can be stepped up using transformers, but I'm not going to go into much more detail regarding that. And if you remember from my previous video, DC actually flows in one direction. AC on the other hand, like it fluctuates. So it's going to be positive in this half, negative in this half, then again positive in this half. So yeah, unlike DC, AC flows in two directions. So now let's understand some of the characteristics that are associated with AC waveform. And it is necessary to understand some of the terminologies because, like now we have digital or microprocessor relays which actually have a capability that they can be hooked up to a computer and you can see the voltage waveforms and the current waveforms, and using that you can actually identify what caused the fault, where the fault was caused. But in order to understand that, it's necessary to have our basic concepts clear. So before that, let's assume that you have a string like this. So let's say you hold it from here and you jack it up and jack it down. So what will happen is it's going to generate like a wave like this which will travel through this string. Now let's say you keep on doing this motion continuously, up and down, up and down. So what will happen is that a waveform is going to form like this, and it's going to keep on flowing through the string. So this is exactly like this AC waveform over here. So the first term that we actually hear is amplitude. So see, consider this as the resting point, and this over here is the peak point. So amplitude is basically how long the wave takes to go from this resting point to this highest point over here and come back over here. So this distance basically that we show over here, this is actually known as amplitude. So basically from the resting point to the highest point is the amplitude. Now the second term that we commonly see is period. So see, basically we want to know that how many seconds for each cycle this waveform will take. So what is a cycle? So cycle is, like it starts like this, it goes like this, it goes like this, and goes like this. So this is one cycle. Why? Because after this, the AC waveform is going to repeat itself in the same form. So this is one cycle. So we want to know how long will this waveform take to go to this positive value, how long it will take to come to this negative value, and then come again to its original position from where it started. This is known as period, which you must have correctly identified is 0.5 seconds if you see over here. So you see, again, I'm just going to repeat it. How long it takes this waveform to go to this highest value over here, how long it takes this waveform to go to the highest negative point over here and come back to the original point. So that is known as period, or you can say, like how many seconds for each cycle. So 0.5 seconds. The third term, which is, like again commonly heard, frequency. So frequency is actually opposite of a period. So frequency basically asks us a question, how many cycles you can have in 1 second per second, how many cycles you can have. So you see, we already draw like this is one cycle over here. Then you have your second cycle, and that's it. You have your 1 second over here. So how many cycles? 2 cycles. So that is why the frequency is 2 cycles per second, or you can say 2 hertz. So frequency is basically equal to 1 upon time, or like you can say period. So I hope this makes this concept very easy, because in India we have like 50 hertz, but many people don't know what exactly is that 50 hertz. So that's like 50 cycles per second. So that is basically what the idea is. Then the last term that you have is wavelength. So wavelength is basically, like the distance that the wave actually travels from this starting point to the end point. So basically this distance over here is the waveform. Now remember, wavelength can, I'm sorry, it's not waveform, it's wavelength. So wavelength can be this as well. You just have to pick two similar points. I'm just going to draw it over here. You can't have like this and this point. This is not wavelength. This is, guys, wrong. Wavelength has to start from one particular point and the same points. You basically need to take same points, and that is the wavelength. So I hope this clears your concept regarding amplitude, period, frequency, and wavelength. So as I mentioned, frequency is 1 upon period time. So now let's look at the peak and the RMS value of AC voltage. You'll hear these terms like what is RMS, what is peak value. So peak value is basically, like this is the 0 point and this is the highest point. So it's just the measure between the lowest and the highest point over here. So this is the peak value, and peak to peak this is the positive peak, and this over here is the negative peak. So this is the peak to peak value. But we have this concept of RMS value, and why do we need this RMS value? I mean, what is the significance of this RMS value? So before understanding that, understand, like, let's say you have a DC circuit, something like this. This is my time and this is my current. So if you see over here, DC is actually constant. So let's say 1 second, 5 seconds, 10 seconds, the value of current is same. If I tell like this is 10 amps, at 1 second it is 10 amps, at 5 seconds it is 10 amps, at 10 seconds this is 10 amps. Is this true for AC? Of course not. Because if you see in this diagram over here, you basically have some different value of current for some time. For some time the current value changes again over here, and current value actually changes again over here. So how do we actually find, let's say, the power consumed by a bulb when there is like AC voltage? So then the idea comes about RMS, which is root mean square voltage, and we'll see like why this is called as root mean square voltage. So let's say you have a circuit like this. Okay, I'm just gonna go, maybe you have a bulb like this and there is a DC current flowing. So we know that power is actually equal to IDC square into the resistance, okay, which we saw that from the previous video. This is the standard power formula. Now this power value for an AC waveform would be different at this point. Would be different at this point because power over here would be I1 square R, power over here would be I2 square R, power over here would be I3 square R, and power 4 over here would be I4 square R. So different values of power. So what we can do is we can say that power in this circuit could be, let's say, P1 plus P2 plus something like this, you can say, and you basically divide it by the number of these intervals. Let's say that is n. You basically taking an average of all these values, and you can then find like the power consumed by the circuit. So what is P1? So P1 I can actually say is I1 square R. P2 is I2 square R, and similarly like this. So now I can say that my I DC square into R is equal to I1 square R plus I2 square R plus divided by N. The resistance on all ends would get neutralized, so I am just left with I DC square is equal to I1 square plus I2 square plus something divided by N. Just gonna change the pen color so that it's become easier. So I'm just gonna take it over here. So then IDC actually becomes square root of I1 square plus I2 square plus divide by n. So this square root is basically this r over here, root. What exactly is this? I1 square plus I2 square plus, all these terms divided by n. You guessed it right. If you have, it's average or mean. That is why you have this m term over here. What is this s? Because you're squaring all the currents, and y square because power is I square r, right? So that is why you have this square over here. So that is why it is called as root mean square. You see, that is the reason why it is called RMS value. Now for a sine wave, RMS value is actually the peak value divided by square root of 2. This is just true for sine sine waveform, not for a square waveform or sawtooth waveform, because they would have different peak values. So, but generally for RMS value, you would have the peak value would be divided by square root of 2 for a sine waveform. And whenever somebody tells you, we have like a single phase, let's say AC voltage equal to 240 volts, this is actually the RMS value that everybody is talking about. So then using this RMS value, you can actually find the power. So I hope this actually clears your queries if you have any regarding the peak and the RMS value of the AC voltage. And finally, we'll see that what exactly is this induced current or induced voltage as they actually say. So, like this basically the Faraday's law of electromagnetic induction. You must have read online, or like it basically states that there is induced voltage in a circuit would be like equal to the rate of change of magnetic flux. There are a bunch of definitions, but I want you to understand that what exactly is this going on. Why do they call it induced voltage or induced current? And this can be actually like very easily understand with the help of an AC generator over here. Again, I'm not going into the details of AC generator working right now. I just want to put the concept over here. Definitely in upcoming videos, when we look at the generator protection, I'm going to go much more detail into how an AC generator works, how a DC generator works, and then like we can look into that. So what happened was, so let's say you have a coil like this, and let's say it's connected with a battery. So a current would start flowing, and it would actually generate some magnetic field over here. So current actually produces a magnetic field. What Faraday thought was, what if I use this magnetic field to actually generate the current? So he thought that what if the opposite is true? That way we would not require this battery over here. I could like use magnetic field and generate current. So he did series of experiments and find out that that is possible. So basically whenever there is a change in the magnetic field, he saw that the current was like getting induced in the coil. So let's say you have a magnet like this, S pole, north pole over here, and let's say you have a conductor like this. I'm just going to show a bulb. So he realized that when you move this magnet over here in this direction, so this bulb like goes on. When you move over here, this bulb goes on momentarily. If you keep this magnet stationary, nothing's going to happen. So if you keep on moving this magnet like this, or if you keep on having a motion of this magnet, there's going to be some current that starts flowing inside this coil over here. So now when you have current, you will definitely have voltage. So because this magnet is actually causing this current to flow inside this conductor, this is actually called as induced current. And because this induced current is present in this conductor, you would have an induced voltage. So this brings us to this basic Faraday's law of electromagnetic induction, which is like used to actually generate power. And three important things are needed for inducing this voltage. First, of course, is you need to have a conductor. I mean, like current just can't generate in air. you need to have a magnetic field, and that magnetic field needs to be rotating. This is very important. I mean, the stationary magnet would not cause any induced current or induced voltage, but there has to be some motion. So see over here, you have this AC generator, you have your windings, and let's say you have a shaft like this, it's connected to this shaft, and it keeps on rotating. So as soon as this magnet is rotated, you see there is actually there is a motion, you can say, which produces the current in the coils, and they travel down through the wire. Now again, like there is no current over here. Again, whenever like the poles change, so the direction of the current changes. The direction of the current doesn't matter to the load, because we want to generate current, but like it's very easy to understand what's exactly happening over here, and why they say like there should be a change in the magnetic field and the flux to generate or induce voltage and current. So this is the basic of like Faraday's law of electromagnetic induction. Definitely in upcoming videos, as I mentioned, we'll look much more into details of the transformers and generators, and in the upcoming part 2 of the video, I'm going to discuss basics about the transformer, inductors and capacitors and their behavior. So this, guys, was a short video to just introduce you the concepts of AC circuit fundamentals that I used in substation protection and control design. I hope you like my video, and please subscribe to my channel. Just put down in comments if you want to learn or if more, or you have some questions. And thank you again for watching my video.